Okay, guys, so probably we should start. So my name is Dmitry. I'm going to present to you something about generative models, especially implicit generative models. So this lecture will be actually split in two parts. I will do the first part, and then my friend Egor, he will tell you a little bit more about, practical aspects of generative adversarial models. And I will actually assume that you know what is a generative adversarial model network, sorry, and we'll not actually tell you about that, but we'll talk about more complicated things. So, yeah, actually, how many of you actually know what is generative adversarial network? Yeah, like almost everyone. And how many of you really tried once to run it? Okay. So let's start. So at first I will do a brief introduction. It will be kind of, introduction of a gun, how you could make it up yourself. And then basically I will tell you what is implicit generative model. And then we will talk about distribution divergences that we will need to kind of derive more implicit generative models. And we will use these divergences to see how the learning is done in implicit models. So let's start. So, okay, consider a classification task where you have two classes. So the density for the class 1 is depicted here with the green curve, and the density for the class 0 is presented here with the blue curve. So basically, when you learn an optimal classifier on that data, for example, at the point x star, which corresponds to this vertical line, what do you think what this classifier will output? So kind of ideal Bayesian classifier will output at the point this, what value? Yes, it will be the probability, but how can we express it in terms of Q of x and P of x? Yeah, there is a softmax in the network, but the question is a little bit different. So, okay, so basically, the classifier will output this kind of value. So it will be Q divided by P plus Q. Basically, the intuition is, yeah, and if you plot the curve for this classifier for every x, it will look like that. And let's take a look at this point where the density for px and py is the same, or for px and q of x is the same, then the classifier gives us precisely 0.5, right? Where the green curve is above the blue curve, then the classifier gives us a value more than 0.5. Yeah, we assume here that the classifier actually gives you the probability for the first class, the class 1. Yeah, and in this region where the green curve is below blue curve, then the value is below 0.5. Yeah, of course, if P of x is exactly Q of x, then the classifier everywhere gives us 0.5. So for now, we had fixed P and Q, two distributions for each class, and trained a classifier. Okay, can we use the output of the classifier to move the distribution Q of x towards P of x? In fact, we can. So again, we use the same logic, right? If the density is the same, the classifier should give us 0.5. And if it gives us something that is above 0.5, we should push or pull the green curve down. Yeah, and if our classifier gives the value below 0.5, we should push this curve up in those points. So that is a kind of feedback we can get from our classifier, and in order to update our model distribution Q. Okay, and yeah, basically, if you do it like step by step, then your green curve will be matching the blue curve eventually. So what do we need to learn a classifier? We only need samples from P of x and Q of x and nothing more. another question we need to solve in order to move Q to closer to P is how do we parameterize the distribution Q? There are two options here. The first one is explicit parameterization. It's like it is done in VAE, for example. You say that, okay, my distribution belongs to a family of normal distributions, yeah, and it is parameterized by, for example, mean and variance of mean and covariance metrics of normal distribution. And the second option is to say that we will parameterize our distribution implicitly. What does it mean? Actually, it's very similar to generator in GAN and kind of similar to generator in VAE. So we take a sample from new normal distribution and apply a function. Oh, okay, so consider a random variable that is distributed, for example, normally. If we apply a function to this to this random variable, then we will get another random variable. And basically, by changing this function g that we apply to our random variable, we can get whole different random variables at the end, right? So that is basically the parameterization. By changing this function g, we get different distributions here. So what are the pros and cons of two approaches? In the first one, we actually kind of define the density explicitly, so we can evaluate it in any point. On the other hand, still, for the learning purposes, to learn a classifier, we need to be able to sample from this distribution. So we cannot take any distribution in here for which we can write down the density, because we need to be able to sample from this distribution efficiently. But on the other hand, this distribution should be expressive, and it's really hard actually it's kind of trade-off for now. So basically, I guess the main problem is small expressivity that you can get in this case. On the other hand, in this case, you actually, by parameterizing this function g with a neural network, you can traverse a lot of functions. And basically, your expressivity is really, really vast. Sampling is easy, but you cannot evaluate Q of x. You can sample from it only, but not evaluate. So yeah, in the case of images, the image you probably saw, if you train a generative model, it transforms, for example, an image filled with noise into one of the faces. Yeah, it's a trained generative model will do it. Basically transform normal distribution into distribution of the faces. Okay, and I have a small simulation here. Basically, it's a GAN, nothing more. So the blue curve is a P of x that we want to match, and the green are the samples from our generator. We do not have explicit density for it, so we approximate it with histogram, and that is how it goes. Basically, yeah, it kind of matches the blue curve. So yeah, how exactly it works in GAN? We have a classifier. Basically, it predicts the probability for the class 1. Then we have a classification loss. Basically, it is log loss used in any classification task. We want our real data from P of x to have label 1, and data from the fake distribution from G, from Q, to have label 0. And the algorithm is the following. So first, we kind of train our classifier till the end, and then we use this classifier as a guide. So we extract a feedback from this classifier, and we update our generator G, do one gradient update. And then again, we retrain our classifier and then do a gradient update. And in the end, we get a generative model, and Q matches P. Okay, what I want to tell you actually that it's not the only option to construct learning procedure for the generator. The first step where we train the classifier, we can actually replace it with whole different things. It should be just a guidance for the generator. It should provide a meaningful gradient for the generator. So let's take a look at several examples. So our classifier, as we already noted, actually computed this kind of quantity for every x, right? So this kind of ratio, and we could use that ratio to guide the generator. Right? We just compared it with 0.5. Oh, wow. Sorry. We could also use this ratio. We just need to compare it with 1, right? Or we could use this difference. Again, if this difference is positive, then we need to move Q in one direction. Then if it's negative, we move it to another direction. And another option is to have a guidance as follows. So consider at every step, we kind of compute the distance between P and Q. Then if we have this distance computed, we can compute, a gradient with respect to generator, how we should change the generator in order to decrease this distance, then it can serve as a nice guide. And basically the step 2, generator update, always stays the same. So we can come up with many different objectives in here. Like it should only generate a meaningful feedback for our generator, and generator gets this feedback and just moves itself closer. Okay, so actually we are now talking about implicit models. So again, implicit model is when we kind of parameterize our distribution Q with a generator and only can sample from this distribution and learn this generator with some learning objective. So in implicit models, density function is intractable, but we should have a way to sample from Q of X. We do it with the generator G. The only requirement we put on the generator G is that we should be able to compute gradients with respect to parameters of this generator. Okay, and another point, as we can sample from Q, we can compute expectations over Q. That is important, and that is basically what we use to learn the classifier, to learn the generator. And generative adversarial network is a particular case of implicit generative models. Just one special example. Okay, if we compare it to prescribed models, for example, VAE, where we specify all the distributions. Yeah, in VAE, we can evaluate and sample all the, we can evaluate and sample prior, then we approximate distribution P of X, our approximated posterior, and so on. So we define them explicitly, and that is why we can do a lot of things with them. In implicit models, well, we can sample and evaluate the prior, yeah? But, well, from P of X, from true distribution, we can sample using our data set. Yes, from Q of X, we can sample using generator, and basically that's it. Then it's really hard to approximate density Q of X, and it's really hard to approximate posterior. Okay, so let's move on. That was a short summary what is an implicit model. So I told you that we actually can use different guides. It should not only be a classifier, so let's take a look what it can be. So you've already seen this slide. This is a gun game, so we have a classification loss, and then we update the classifier, then we update the generator. Let me rewrite it a little bit. So instead of minimum of L, it will be a maximum of minus L in here. Nothing changes in here. And what is interesting that basically this maximum turns out to be equal to this constant plus 2 divergences between P and Q. And that is very similar to this feedback variant that I've shown you. Like if at this first step we compute a distance between two distributions, then we can use this distance as a guide, right? And it turns out that we can think about the GAN in two ways. The first one is that this classifier computes, point-wise ratio, and the second one is that it kind of computes the distance between two distributions. Okay, so now when we understand that by maximizing this loss over all possible functions that we parameterize with a neural network, we get exactly distance. We can ask ourselves if we can, it's actually what I just was talking about. We can ask ourselves a question if we can come up with a different loss function that probably lead to, another divergence in here. So here we have like two Jensen-Shannon divergences. There are a lot of ways to compute distance between distributions. So probably by changing L, we will we'll basically get another kind of divergence in here. So yeah, and let's now discuss some divergences that actually allow this formulation. It is called actually a dual formulation. The formulation when the divergence is computed as maximum of something, maximum over functions usually. Okay, yeah. So we will talk about f-divergence, integral probability metrics, and optimal transport. So what is f-divergence? Basically, this is a definition. It looks very similar to Kyle divergence, and in fact, Kyle divergence is actually a special case of f-divergence. So f-divergence is parameterized by a function f. Function f, it's called generative function, and it is just a convex lower semi-continuous function satisfying f of 1 equals 0. So basically, you can come up with a function that satisfies those requirements, and it will be another divergence. Just for your information, this is an image from Wikipedia. This is lower semi-continuous function. It's not convex, of course, but so lower semi-continuous means that if you have discontinuities in your function, then this function should be defined from the left side. Okay, so yeah, talking about primal and dual formulations, so this is a primal formulation. And the problem with this formulation for our case that it requires us to evaluate the density at every point in order to compute this divergence. And basically in implicit model, we do not have at least Q of x, and well, P of x we also don't have. So, and the dual formulation, as we will see, will not require us to compute density, but it only will require us to sample from distributions P of x and Q of x. So let's, oh yeah, just a little bit of special cases. So this is f-divergence. Again, if you use f t log t, then you will get KL divergence. If you will use minus log t, you will get a reversed KL divergence. Then if you use f of t like that, it will be a total variation metric. To derive dual formulation, we need to say something about Fenchel Conjugate, because it will be used. Actually, well, I want to tell you about Fenchel Conjugate, like intuition about it, but nothing more than definition will be used in the derivation, but it's really important and interesting thing to know, used a lot in optimization, for example. So consider a function of f of t. Be sure to understand that the axis here is t, and the function of t argument, and x arguments sits in here. So Fenchel conjugate is basically a function that is computed for every x as supremum of something, and supremum is taken over another argument. So let's take a look what it is. So we have a function f of t, and inside here, we basically have a difference between linear function, t of x, and our function f of t. We assume now that x is fixed just for the explanation. So this is our linear function, and this is our f of t. And what we basically do, we try to we try to find a point where this difference is the maximum. For example, this maximum is attained at this point t star. So the difference is a minus b, okay? And the interesting thing is that x, the slope of this curve, is exactly the gradient of f of t in the point t star. And it's really easy to see. So if t star actually maximizes this quantity, let's just write the definition of supremum. So just take the gradient of what's inside with respect to t and set it to 0. It will be like that, and then we just derive that x is exactly gradient of f of t in the point t star. Okay, so basically, this Fenchel conjugate, if in a point x it equals to t star, it means that a line with a slope x supports f of t at t star. Supports, it means that basically the function f of t has a gradient equals to x in the point t star. Yeah, so why actually do people use this Fenchel conjugates? It's especially useful in convex analysis. Basically, for any convex function, you can either describe it with the function itself, like the value as a function of argument, or you can describe it with a set of supporting hyperplanes. If for each point you know a slope of a hyperplane that supports our function, then by using this information you can recover the whole function. Yeah, it's not true for non-convex functions, but yeah, that is basically the main case. So this was a bit of intuition. We will not use actually this intuition at all. Probably in other random facts. So Fenchel conjugate is defined as that. If you can compute a conjugate for the conjugate, it will be a B conjugate. And for convex lower semi-continuous functions f, B conjugate is equal to conjugate. Yeah. Okay, so let's derive the dual form. So this is a definition of Fenchel conjugate. This is a definition of f-Divergence. We first just rewrite the f-Divergence as an expectation, yeah, integral turns into expectation, and then we use the definition of Fenchel conjugate in here. So take a look, this was an argument of our f, so it replaces this x here, so we have t times p divided by q minus f star. And then we want to basically swap this expectation and supremum. And we can do it actually. Why so? So in here, what we do, we basically sample x, and then for this x, we look through the t space and find optimal t. Then we take another x, and we get another t, and so on. So we kind of find a function, t of x, right? That for each x gives us t. So we can do it kind of explicitly. So we can say that, okay, well, we will search through the functions, all the possible functions like t of x that gives t using x, and only then we will sample x's and test whether it gives us the supremum or not. So it's kind of equivalent, right? So now we are looking for the function instead of searching for a scalar. And it instead of t here a scalar, we have t of x here a function. Yeah. In here, we look through all possible functions. And if we limit the space of the functions, we should put greater or equal in here. So that's it. Basically, we already constructed the dual formulation. So this was a primal formulation. And now we say that, okay, this d is greater or equal than this supremum over some quantity. Yeah? And actually, the bound is tight for this function. So we can analytically maximize this function. If just we put this expression instead of t, it will be exactly, exactly the value of divergence. Okay. Another metric that we want to consider is the integral probability metric. Basically, it's defined like that. It's very similar. So we have a supremum over the functions of some statistic of distribution P and the same statistic of distribution Q. So basically, it's the largest difference between the statistics, and the statistics are taken from some family of statistics. And yeah, for some families, these are denoted with calligraphic F. For some families, it's not a proper distance because it will not satisfy, properties of the distance. And for some families, it is a distance. And basically, for example, if you choose your family to be all the functions, all the Lipschitz functions with the Lipschitz constant less or equal than 1, then it will be a Kantorovich metric or Wasserstein distance. If you take this family, all the functions with L infinity norm, well, not in L infinity, but just infinity norm less or equal than 1, then it will be total variation distance. So basically, by changing this family F, you will get different distances. Again, just to compare, this is IPM. it looks like that, and this is dual formulation for f-Divergence. It looks very, very similar. The only difference is we have the same statistics in here, but slightly different statistics in here. It's t of x in here and f star of t in here. But that's basically it. The last way to measure the distance between distributions is, well, that I want to tell you about is optimal transport. Basically, it's always explained as, you know, Earth movers distance. When you have two piles of sand, and you basically need to, you know, transform one pile into another pile. And, well, you're lazy and you do not want to do extra work, so you want, well, you want to move kind of as, I mean, just consider this experiment. You just, you know, yourself take a pile from here, I mean, a piece of a pile in here, and then, you know, go by your feet and put this pile to another place. And you want to minimize your, you know, your feet work. So basically, you define a cost function that expresses your kind of, you know, energy that you spend on transforming, on moving a pile to another place. And you say that, okay, I want to transform the pile into this shape, but I want to spend as little energy as possible. And formally, it can be expressed as this kind of thing. It looks really, really scary, actually. So, but what's happening in here? First, we are looking for such distribution gamma. It is joint distribution defined on the joint, you know, space of P and Q, but it is a distribution that has marginals P and Q precisely, and nothing more. So we are going to look for this gamma in this family of distributions with proper marginals. And then we kind of, for example, let's test one gamma. We pick a gamma from this family, then we sample points from this gamma, and then we compute the cost, the energy that we spent on transforming one pile into another one. So what does it mean? Actually, gamma tells us which point in one distribution should be transformed, I mean, from which point we should take some quantity and transform it to another point in the second pile. Let's take a look at the example. So for example, this is one distribution, this is another distribution, and this is basically optimal gamma. It tells us that this bar should be basically transferred into this bar and this bar. And like the color actually shows the amount that should be transformed into this bar and the amount that should be transformed into this bar. Yeah, and for some gammas, again, we do infimum over the gammas here. It's kind of infimum over all possible transportation plans. And the optimal transportation plan that minimizes our cost is basically the distance between the distribution. Yeah, if the two distributions are equal, then the cost of transportation is exactly zero because we do not need to transport anything. Okay, so this is a primal formulation, and it happens that it has a dual formulation, and it looks like that. And basically, it's just a special case of IPM with a special family in here of Lipschitz functions with a Lipschitz constant of less or equal than 1. Yeah, just to give you a sense why actually people need all these different divergence metrics, why don't we have one of them only? So their properties are a little bit different. Consider this example. So we have two random variables, V and Q. V is basically uniform distribution defined on this segment. So we have a 2D plane, and V defined as a uniform on this segment. Okay, and Q is defined on as a uniform on this segment. Basically, it has a coordinate theta as a first coordinate, and the second coordinate is stochastic. So if we can compute the distance between these two distributions, then all these metrics will give us different values. But what is important, actually, if we have a continuity with respect to theta. So consider like theta equals 1 and theta equals to 100. Intuitively, when theta equals 1, two distributions are closer than in the case when theta equals 100, right? But for example, Jensen-Shannon divergence and KL divergence really do not depend on theta at all. So they will not tell you the difference between those cases. But Wasserstein distance, actually, it is continuous with respect to theta. So you change the theta, like in the case when theta is 1, then this distance is exactly 1. And if theta is 100, then this distance is 100. So it's kind of good from theoretical, at least, perspective. Okay, so a little bit of summary. We've looked at f-Divergence. This is a primal formulation, and we can derive a dual formulation. Integral probability metrics, it looks very similar to dual formulation of f-Divergences. Again, we have a supremum of, well, it's the largest difference of the statistics. And optimal transport, again, we have a scary primal formulation, but we can reformulate it. And the dual is actually IPM, a special case of IPM. Okay, so now when we have several divergences and their duals defined, we can easily use those duals and plug them into our learning procedure. Yeah, basically that's it. So we just say that, okay, our minus loss is a dual for some kind of divergence. And then, well, our game is kind of minimum of maximum of minus loss. It is the same as minimum of divergence. Yeah, minimum over the parameters of the generator. So at every generator step, we will be minimizing some divergence between two distributions. And at the first step, at this kind of update step of the classifier, we will compute this divergence. Okay. So for example, for f-Divergences, so this is a dual formulation. So what we can do, we can parameterize T of x with a neural network. Yeah, it will be just a neural network that will output, for every x, it will output a value, a scalar value. Yeah, so our loss is like that. It's just a dual, yeah, and then everything else stays the same. So we just changed the loss slightly and didn't change anything else. Yeah, so we could go slightly different way for f-Divergences in terms of parameterization. So this is a dual for f-Divergence, yeah, and I've told you about the fact that actually if we take t like that, so f prime is the gradient of a function f, and we know it, and put this thing into the supremum, basically we will get precisely the divergence. But the thing is that this f depends on something that we actually do not know, this r of x. And now, instead of looking for t that attains a supremum, we can look for a function r that attains a supremum. So our objective will look like that. Basically, we put t inside of this formulation and change our optimization space from t space into r space. Yeah, and immediately we get another loss for training our generative model. Yeah, everything else stays the same. So that was basically about define some loss that gives you a guide, and then use this guide in order to train a generator. Yeah. And another way to learn a implicit generative model is to do ratio matching. So ratio, as we already understood, gives us a feedback to our generator, right? We just compare it, well, I mean, if we're talking about this kind of ratio, we compare it to 1. If it's greater than 1, we update Q in one direction. If it's less than 1, we update it in another direction. But how can we estimate this ratio Q, this ratio? The first option is to use classifier. We've already seen that in the GAN. And here is another option how to do that. We can actually say that, okay, the true ratio between distributions P and Q, we do not know it actually. And we want to approximate it with a neural network with parameters phi that take a point x and actually outputs a ratio directly. So what do? We minimize the expected distance between the ratio produced by our neural network and the true ratio, even though we do not actually know the true ratio, but it will be okay. So let's do a little bit of derivation. So basically, just open this expression. We have the first term squared, then like 2 times this one times 1 over 2. Then there is no 2 or a coefficient here. And I just rewrote expectation as integral with q in here. And we see that this q cancels out with a q from r star. And then this term is exactly expectation with samples taken from p of x of our neural network r phi. And the last term, which is kind of a squared, this term, r star, it is a constant with respect to our neural network r phi, so we just do not use it to update our network r phi. So basically, we just derive another way to learn a guide that gives us a ratio at every point. And then we will use this ratio to update our generator later. Okay, so that is basically it. If you have any questions, I think we have several minutes till Egor will start his presentation. For those of you who do not have any questions, you can probably take a break and return in at most 5 minutes from now. Okay?
My name is Egor Zakharov, and I'm going to continue Dmitry Ulyanov's talk about implicit generative models, but we will focus more on the practical side aspect of them. So first we'll discuss the adversarial objective and how it is optimized in practice, so this divergence that Dima was talking about. And then we will discuss some of the tricks that are used in GANs in order to make this optimization process more stable and convergent with higher ratio of success, and some practical applications in the end. So first of all, let's start with problem formulation once again. We have some distribution P of x and well, samples x, which usually come from some high-dimensional complicated distribution that we want to approximate, and well, we don't want to approximate, we just want to sample from it. And in order to sample from it, we just take a distribution, well, which is either simple, like a normal distribution, or just some other data set, which, well, we can also sample from, and learn a mapping, parameterized mapping between these two distributions. So Q of x has the same support of P of x, and we want to make it as close to P of x as possible. So for that, we're going to use divergence. This is like the same objective that you've seen on the previous, on the previous talk. So this objective essentially measures the distance between real distribution and generated distribution, the distribution of generated samples. And essentially inside we have minus binary cross entropy for classifier f. So if we consider f to be a classifier with outputs a probability of the point that of its input being from real distribution, then it outputs 1. In another case, it should output 0. And for that objective, we're going to consider optimization problem for g theta, which, well, we just have to replace it with the optimal value for f star. So this is like the Oracle classifier, which is the solution of this problem above. And let's, for that problem, consider an example of how this optimization process will, problem will behave. So we have a distribution of P of x depicted here, Q of x here. So the colors and distributions are switched compared to previous lecture for illustrational purposes. And we have some optimal classifier that distinguishes between samples from these two distributions. And what we would like to do, we would like to push the distribution of generated samples upwards, right? So that it would match the distribution P of x. So, well, we already have optimization problem that we need to solve in order to achieve that. We have, as g theta, we usually take, well, neural networks. So this is like a parameterized function space that we use. And to optimize neural networks, we need gradients. So let's compute the gradient of this objective. So the first term, it does not depend on theta. Well, second term, First term does not depend on theta. Well, we can take the gradient with respect to second term, and using simple chain rule, so we first differentiate with respect to logarithm, we get 1 minus 1 divided by 1 minus I minus f star. Then we differentiate f star with respect to its argument, which we denote as x, and then we differentiate the argument with respect to parameters. And what you have to pay attention to is this multiplier that we have for each term inside, well, the gradient. So we evaluate this expectation at, well, basically we approximate this expectation with some samples z and evaluate it. And for each sample that we have this multiplier. So this is if for each sample this multiplier is 0, so we will have no gradient. We won't be able to train our well, neural network. And let's see how this multiplier looks in this practical example. So we can just plot this curve, right? And we see that, well, we just sampled from the distribution Q of x, a couple of points. And we see that for most of these points, well, in our case at least, this multiplier will be 0. So essentially what it means that these points will not contribute to the gradient at all. So the value of the contribution of these points will be 0, while these points will contribute, well, with large like weights, you may say. And essentially in our case, well, this behaves as we want. So we think that this point is more important. So we want our distribution to push upwards like higher at that value. Well, and these points are in this case not important. But well, you can already see where the thing might break. Let's consider the example, a different one. So we have two distributions, P of x and Q of x with disjoint supports. And if we plot our optimal classifier, it is like, well, very certain. So it is flat almost everywhere except this narrow region. And if we just sample a bunch of points, we will have 0 gradients at these points. So if we just are unlucky, and for our, well, so, yes? F is a classifier, but it is also like a proxy to ratio. It is a ratio between P of x divided by P of x plus Q of x. So this is an optimal classifier between these two distributions. The answer was, the question was, what is F star? Yeah, for now we just consider it as, well, an optimal F star. So this is the perfect classifier that we would get. And later we will see how it is trained. So, okay. We see that at these points, we just got unlucky with our stochastic gradient descent, and we will have 0 gradients, so we won't be able to optimize it. And only like at this point, which is, well, highly unlikely, or other points from the left tail of the distribution, we will get some gradients and we'll be able to optimize. Well, this example may seem like very toy and, well, hand-picked failure case, but in multidimensional case, where P of x and Q of x are defined over, for example, image space, where you can imagine that if we want to sample, for example, photorealistic images of cats, we have very, well, low probability to initialize our neural network that will produce images that will look similar to cats. Probably will have also disjoint supports. So this problem leads us to a very slow optimization process in the beginning when we only start training, when we optimize divergence. And let's consider another toy example. So we have the same problem, and for P of x, we will consider a mixture of Gaussians. So we will, in order to train F star, we will parameterize it with another neural network, D. We call D, well, discriminator, G we call generator. And instead of F star, we'll consider the optimal set of parameters phi star for that network, which is the solution of this optimization problem. And we just will use also gradient descent till convergence to solve that internal optimization problem. And let's see how it behaves on practice. Okay. Okay, one moment. I'll restart it again. Okay, so here we have our initial distribution P of x that we want to sample from. This is initial distribution Q of x. This is initial classifier, and that's an optimization process. So we'll run it for the fixed number of iterations. We see that the convergence at the end becomes very slow, as well as the beginning. So, well, what I listed is just one of the problems. What I said before is just one of the problems related to that objective. So let's see it one more time. And we see that in the end, we don't even converge to the true distribution. And so this is like not unexpected, because on practice, GANs are not trained using the divergence objective. So on practice, we're using something different. And this algorithm is called alternating gradients. So it's quite simple. Let's consider our objective one more time, but this time we'll explicitly write the divergence. So this will call a loss function, which depends on two groups of parameters, theta and phi. And the previous algorithm that we used, we optimized to convergence of the internal optimization problem with fixed theta, and then did like a step for theta, and here we had divergence, because this is an optimal value. So we minimized the divergence, which we just ran, and saw that it fails. And let's consider the alternative algorithm that is actually used to train GANs. It's just so we just alternate between the updates for the group of parameters phi and theta. So here we go up the gradient, here we go down the gradient. This objective actually works quite well. In the optimization process actually works quite well, as we are going to see. But the problem, intrinsic problem with that, is that we are minimizing lower bound for divergence. So I want you, for a moment, to think about it. So here we have an optimal value, argmax. So here we have suboptimal, so it's lower than the true divergence. And we want to minimize it on the second step. So minimization of lower bound does not tell us anything about minimization of the true divergence, in contrast to maximization of estimated lower bound when we do, for example, variational inference. So this is, well, quite an assumption that we make, but let's see if it actually works on practice. So we ran for the same amount of iterations, and we see that it actually starts to converging, and like in the middle of the optimization process, it's actually mimicking the true distribution quite well. And well, in the end, it converges to the true distribution, starts fluctuating a little bit. And what I want you to pay attention to is the fact that classifier is very suboptimal at all the steps of this optimization process. So it's the lower bound for divergence is not just like lower bound, it's very loose lower bound. So it's very far from being optimal. But this works, and this is what is actually done in practice, and is one of the like hot topics related to GANs. Yes? Well, the difference is actually here. These are two algorithms. First algorithm does not converge in the video, and second one does, and does it much quicker. This is a good question, and I don't think that, well, people can answer you why. This is actually essentially a question why GANs work. Why does this algorithm actually work? Well, it's just empirical for now. We don't have a very, very good explanation of why. But essentially, I'm just trying to hint you what I was telling you that for is that minimization of divergence does not work well with neural networks because of extremely slow convergence speed and the fact that the convergence is not really guaranteed, and that GANs that we use are only inspired by the divergence because we minimize the lower bound to divergence during optimization process. And we also optimize GANs with alternating gradient descent. So if we use that for games, so min-max problems, the convergence to the optimal point is not guaranteed. So, well, this is just the optimization problem related to that algorithm, and we need extra tricks applied to be able to converge with, well, higher success ratio. So one of the tricks that we are going to use is, for example, well, we need Now I'm going to describe you some like empirical tricks that are used by people, and we'll try to provide some explanation of why these tricks used. But the primal explanation for these tricks is just empirical performance. So if you run with your neural network with that trick or without that trick, you will get much better performance. First of all, well, what people suggest you to do is to use prior knowledge. So for example, if you know that your distribution have strict support, for example, in terms of images, you have a compact support, which and the output of your neural network, if you don't put any nonlinearity in the end, is, well, basically a real plane. So in order to make the training like easier, and in order to introduce that information inside the network, you can just put a nonlinearity at the end, which also maps your outputs to some compact set. Another thing that people use is avoiding sparse gradients inside the discriminator. What I mean by that, modules like ReLU, so rectifier linear unit, actually put 0 well, for half of the values. So it's 0 if it's less than 0, and x if it's more than 0. And if you put, well, I'm trying to, and essentially when you do backpropagation through that module, you have, well, a good chance to just put 0 into your gradient, and it will not propagate further back into the network. Same with max pooling, when you just put zeros in, well, for example, if it's of the size 2, you put zeros in 3, okay, so I guess everyone knows what max pooling is. And it is suggested to replace those modules with their like dense analogs that do not zero out the gradients. And this helps with intrinsically smooth domains, for example, signals and images. And one of the problems it may cause is, well, it's also caused by, well, other modules in the neural network, but still. So we know that images are, well, rather smooth with boundaries, but they're smooth, like in the bottom row. But when we use this, when we zero out the gradients, what we end up in the end is zeroing the gradients that we train the generator with. Right? And if these gradients are that we use to train the generator, so with respect to generator output of the loss, are sparse, so they are very discontinuous. So in the end, what we are trying to do during training is, for example, passing gradients through one of the pixels and not passing gradients through another pixel. So we essentially want our neural network to make discontinuous images, which turns into bad performance on practice. Now, well, coming to the next topic, I would like to ask you a question at the end of this slide. So we have still our objective, and we want to optimize this objective. So we compute the gradients with respect to phi. This expression you have already seen. No, almost, right? This is just simple chain rule applied to both of these expectations. And what we would like to do, we would like to just denote outputs, denote real data and outputs of generator as some combined distribution x hat. And to sample from that distribution x hat, we'll just use the simple chain rule. So we will introduce labels. So for real data, we'll introduce label 1. For fake data, we'll introduce label 0. So it's trivial to sample from that joint distribution. We'll just sample label, which is uniform essentially. So this is 0.5, this is 0.5. And then, well, if you sampled label 1, we just sample from real distribution. If you sampled label 0, we'll sample from fake distribution. And I did this to just, well, it shouldn't have appeared all at once, but let's look at the first line. I did this just to, well, we said before that this is minus by binary cross entropy for the discriminator. But when we train a discriminator, we don't have these two different sets, two different terms and two different expectations. We actually have one expectation over the joint distribution. So when we train a classifier, we have our data x, we have labels y, we just sample data and the labels, and then do like, well, backpropagation through the objective. So that's exactly what I did here. I just replaced two expectations with one. And here we have like indicator that label is 1. We use that gradient in that case and that gradient in that case. And the same value for the generator. It does not change in that formulation. And now a question for you. Is this procedure correct for any choice of discriminator? I would like to tell you the answer. It is no, but I would like you to think for a minute about the example where this procedure will fail. So where replacing that gradient with that gradient may actually alter the objective. Yes? Excuse me? No, not really. It has to do with architecture of discriminator, the particular modules that you use inside of it. Yes, that's correct. I'm actually quite glad that someone guessed. So the answer is if you use any like modules inside that use statistics over batch, it could be batch normalization, it could be some different normalization layer, but if you average statistics over batch, it actually, well, does not correspond to each other. And let's see why. Coming back to our previous example. So in the beginning of the training process, when we have two different distributions for real data and for fake data, when we feed them through the network, we keep that discrepancy between these two distributions. So this is very likely that we will get the activations that also look like that with two pikes. So one pike for generated data and one pike for real data. And when we optimize with respect to, well, using that gradient averaged over, well, combined distribution and use batch normalization inside, we actually average over real mean value and generated mean value. So, well, these values are actually the true values of distribution, right? When we sample batch, so the true value or the true mean value for the distribution x hat is somewhere in between because we sample with probability 0.5. And when we sample a batch, so our, I'm sorry. I think my pointer, okay. So when we sample a batch, our mean values for, well, inside the batch will be proximate to that value, which is somewhere in the middle. Of course, it will have high variance, but still it will be like proximate to that value. And when we do backward pass for generator, we use, when we feed forward, we only feed real data, so because fake data, because with respect to real data, we don't have gradients at all, we have 0 gradients. So we will get a mean value that is different, essentially. Well, in theory and in practice, we will also get like values that are, well, samples that are different. Of course, well, and yeah, this is why I denote this like a function when we backpropagate through the backpropagation of the discriminator. We have one function with mean value here, this one, and also like variance, which is also different. I just showed you the means. And for generator, we have a different one. So you may also tell me that, but Egor, batch norm is supposed to work like that because it has very high variance. So if we just sample a bunch of points from a real or complicated distribution, we will get a very high variance estimate of this generator, and it will not matter. Well, you are correct. So if we do bias variance decomposition of difference between, of expected square of difference between these two values, it is indeed has these huge variance terms. But in practice, we have some objectives. It does not work for all GAN objectives. For example, it works for non-saturating GANs that you are going to see in practical part after dinner. If you, here, it actually matters. So it actually makes your GAN not converge if you use different estimates during training of discriminator and generator. So if this term dominates these two terms, so this breaks. And a common suggestion, well, yeah, if this, okay. It depends on the objective and the architecture that you use. And so recommended, just for all training of GANs, just to not mess with this, is to actually use the first form, so with the first gradient. So first we sample the data from real distribution, feed it through the network. For this term, we use mu real and sigma real. And for this term, we just use, well, mu generated, sigma generated. And during training of generator, we also will use the same like mu generated and sigma generated in that part of the objective, which generator influences. So essentially, we optimize the same objectives for generator and discriminator that way. And finally, what I wanted to say is that it is when you most of the successful applications of GANs are achieved when GANs are not used like, well, for the sake of it, so as a main part of the problem. We could just pick a well-defined problem and treat GAN as just a trainable objective. So we already said before that we don't really have this intuition about the divergence between the two distributions. So, well, we may as well treat it as just another loss in our machine learning problem. And, well, this loss is unsupervised because we don't need any supervision for that. We just need real data and generated data. And a good example of, well, where this approach actually, well, works well, but there are many more, but this is one of them, is super resolution. So we are given, the problem is following. We are given low resolution image and we want to obtain a high resolution version. So the objective is quite trivial. So we just use our generator to map from low resolution to high resolution. We have ground truth, usually in that kind of problems. And we just minimize like any norm between these two images, between these two images with respect to parameters. So this is a well-defined problem, and we can find an optimum with respect to that. But let's see what happens on practice. So when we have like ground truth image, I don't know, I will hope that you are going to see that on projector, but on your monitors, you will see that in more details. This is like a ground truth image, which is very crisp. But when we optimize with respect to, oh, you can see, when we optimize with respect to mean squared error, we're getting a very blurry image. And this is not related to like our optimization process or whatever. It's just the property of mean squared error that when we optimize with respect to it, we will get a blurry image. Just because on low resolution version of the image, we don't get enough information to produce all these details. And when we just introduce another term, GAN, into the objective, we get crisp image once again. Well, you can see that on the snake much better than this picture. And I will go and talk briefly about it because I think I have a little bit more time. So it is actually intrinsic problem related to super resolution. So if we want to minimize mean squared error or any like estimates based on mean squared error, we will always get blurry images. And obviously this image, when we introduce GAN, is suboptimal with respect to mean squared error. So we introduce some information into the image, which is, well, actually pushes us away from the optimal objective. So this is like a trade-off. If we want to get crisp images, we have to introduce some sort of GAN objective or other like similar objectives and produce suboptimal results with respect to, well, you may say content. Yes? It helps, but not so much. What helps is applying like matching of features of pre-trained encoding network, for example, perceptual loss, that helps. But applying loss directly to the image does not capture like, we assume that every pixel in image is independent when we do that. And this is like a wrong assumption, basically. So let's go on. So to summarize, I would like to say that, well, to make optimization process converge close to saddle point, we need to tune a lot of hyperparameters. So what I just told you before about batch normalization, about like some layers inside the network, these are all hyperparameters that you essentially need to tune. And well, the moral of the story, one of the main morals, is that git-clone is your best friend. A lot of, basically, paper on GANs is released like every week. And a lot of them have code on GitHub. If you have the problem, you just have to find a paper that solves similar problem. Find a paper with repository. Just git clone it and use the parameters. It will save you like month of fine-tuning. Well, and another general things that are not problem-specific is like using separate batches when you're training with normalization layers and combining adversarial networks with other objectives. This one is actually works surprisingly well, and there are a lot of results. You've already heard about CycleGAN and all the related stuff. It just does exactly this, combines with supervised objectives and gets very nice results. And now to the applications. So, as I said before, when we train our GAN, it's not actually mapping like normal distribution into some other distribution. We can use any distribution you want for that matter. And in that case, in the case of this paper, they just used text. So we can sample from text, right? We can just type a sentence and it will be a sample. We can encode that sentence into some, well, vector space and use that vector embedding to just generate images. And another cool trick that they use, which is applied in many papers in, for example, this year to obtain state-of-the-art result, which is basically reinvention of some old trick, is just doing multi-stage process. So first they map from this distribution to the distributions of some low-resolution images that are of poor quality. And then they map distribution of low-resolution images to high-resolution images. So they do that in multiple stages. And this approach is very fruitful when you're working with images. So you can just, for example, like generation of faces, like state-of-the-art results also use, this multi-scale, we may say pyramidal approach. I can tell you many more examples. So this is quite nice, and the results are also nice. Like, for example, this bird is blue with white and has a very short beak. You can see that this is blue, white, short beak. So it works pretty well. Another application that I would like to mention, this is the problem that I was working on. When we're talking about GANs, for example, this one, like, where could you apply it in practice? So it's very hard to find the application, actually. Yeah, the right entertainment applications, obviously. Yeah, that's closer to what I was trying to tell further. But most of the applications for GANs are just for entertainment. That's just fact. So people don't know any applications that are actually useful in some case. And there is an area of research which actually tries to, there are multiple areas, this is one of them, that actually tries to make GANs useful for science, for example. And the problem is following. We're giving a particle in high energy physics. So for example, we have an experiment like Large Hadron Collider, where a lot of particles are colliding and producing the remnants. And we would like to detect the types of the remnants. So basically screen the information from them. And each particle, when it has some properties, for example, the momentum, the type of particle, etc. When it flies into the detector, it produces that kind of response, which is a shower. And basically what happens, the particle just dissipates inside into many other particles. And they deposit energy and produce that shower. So there are a lot of latent unobserved variables in that process, which relate to quantum stochasticity and the stochasticity of particle interacting inside the detector. And what we would like to do, we would like to just, given the vector of known data about the particle, just produce some response, which is, reasonable and realistic. You could use physical model for that and simulate real physical equations. Well, this is the best quality that you could get, but sampling is very slow. So it may take months to generate data to evaluate, to compare it, for example, to LHC data. And alternative approach is just add GAN to it. It's rather, this is one of the possible approaches. I'm not saying that this is the only one, but you definitely could apply GAN for that problem. So you have some vector which encodes the particle information. You have some latent variables that you can sample from normal distribution, and you just map them and, map them into another distribution of these responses. So training takes days, but sampling is almost free. So a lot of data can be sampled in no time. And approximation quality needs to be, still verified in order for it to be consistent with physics. And let's see, check the examples. So these are real data. This is simulated data. So we see that the direction of the particle is very nicely captured. The width, which denotes the energy, is also nicely captured. Here are more examples. And I was talking about validation. So let's see how it can be done in that problem. So in images, it's always a difficult question. So if you sample a cat, how you tell if that cat is realistic or not? There is a real big problem with metrics in that area. For example, in super resolution, you could measure PSNR, for example, and compare PSNR. In GANs, it's harder to come up with such universal metric. But in that problem, you can do that, and we will use this theorem that you've already probably read to distribution match if and only if all their statistics match. This is very informal, but this is true. And if we assume that during GAN optimization process, we actually somehow match the distribution P of X with generated samples Q of X, we will see that if we measure some statistics, they will match also. And here we see that, we almost achieved that. And for many statistics that physicists are interested in, we obtained tighter matches. So this is like a very cool example of how GANs actually work. Because when you optimize GANs, you are not actually embedding these statistics inside the optimization problem. You're solving it in a supervised way. But in the end, you achieve the tight match for those. Well, you just compare the samples of GAN with samples from the test set. All right, and to summarize, well, what I would like to carry with you after my talk is that GANs cannot be explained only by divergences. So as we saw, we don't really get this divergence on practice. It may serve us as a good explanation in theory, but on practice it's not. Training requires a lot of hyperparameters. Use git clone, and well, if you want really good and quality practical results with GANs, just use some supervision. Use supervised objective and add GAN to that, if that makes sense. And then you will get better results. So yeah, that's the end of my talk. Thank you. Now we have like 8 minutes for questions, and if you have more questions, you can ask them during the seminar that we will have after dinner. Yep. Can you repeat the beginning of the question? Generalized. It's hard for me to answer that question. So I would like to learn about that thing because I can't answer you. Sorry. Yes.
Just to vary the first part of the talk and the second part of the talk, what can you say about different measures of quality which were told in the first part of the talk by Dmitry?
You mean divergences?
Yeah, which were bets and
Yeah, this is a very good question. And it seems that there is no really real difference. So if you just apply any of the f-divergences, well, take a sample of those, which are, well, pretty good, and just compare the performance. It does not change. And also, even for Wasserstein gun, well, Wasserstein guns are known for very good performance. And essentially, it seems like this good performance, it has only to deal with the gradient penalty that they're using. So this regularization of the function, so Lipschitz 1 discriminator, essentially. And if you just apply Lipschitz 1 penalty for any other GAN, it will also, well, work well. I mean, not GAN, but divergence, yeah.
but I heard that when we use Wasserstein gun, it doesn't deal with long elements.
Yes, I said that, but I just said that it probably has to deal with the fact that we're using gradient penalty for discriminator. Well, gradient penalty is just enforcing Lipschitz 1 constant for those who are unfamiliar with Wasserstein guns. Well, if you don't have any questions, well, thank you again. And see you on the seminar for those who will come.